Here we want to reconstruct the functional data related to our experiment. To do this, we'll use the project wizard, and for project type we want to choose FMR project. We are using the DICOM file format, and for project name we want to start with the subject ID followed by the run number. When we browse to the folder containing the DICOMs, we can choose any of these files, and Brain Voyager will tell us what scans are contained within this folder. From the list we want to choose the 252 volume FMR, and Brain Voyager will read from the DICOM header file all the information it needs to reconstruct the FMR. When we reach the number of volumes window, Brain Voyager will ask us if we would like to skip any number of volumes. You can read from the text that this is to avoid magnetic saturation effects that occur at the beginning of each scan. If your scanner doesn't do this automatically, it's recommended that you skip at least 2 volumes. To show you the effect of not correcting for magnetic saturation effects, we'll create this FMR without skipping any volumes. Once the FMR is reconstructed, we can close the info pane and take a look at what we have. You can see from the FMR properties that this FMR has 25 slices, and you can see these numbered in the rows and columns to the left. Further reading of the FMR properties tells us that this data was collected at 3.5 by 3.5 by 3 mm resolution and also has a TR of 2 seconds. If we use the left mouse cursor to click and drag a group of voxels on any of the slices, we get this region of interest signal time course window. This window is shown as the average bold response for this group of voxels across all of our volumes. You can see in the first 1 or 2 volumes a very high bold response. This is what we're removing when we skip those 2 to 4 volumes during FMR creation. The effect of not removing these volumes is it artificially inflates the mean bold response, reducing our statistical power for any analysis we hope to do. We can see the effect of this if we do a basic general linear model analysis. But first, Brain Voyager needs to know which part of the signal corresponds to which condition in our experiment. This is done by attaching a protocol file to the FMR. The protocol of the experiment can be defined manually in Brain Voyager. However, typically it's better to create log files from your experiment and then use custom code to convert this into a protocol file. We will cover how to do this later, so for now we will use the protocol file that Brain Voyager provides for this data. We can do this by clicking on Analysis and then Stimulation Protocol, and then loading the PRT provided in the Prepared Files folder. Once the PRT is loaded, we can now see the conditions that exist within this experiment. In this experiment, we have a condition with images in the left visual field, a condition with images in the right visual field, and also a condition with images in both visual fields. You can also see that these conditions are uniquely colored. We can see when these conditions occurred if we click on the Show Plot button. You can see from the plot that these conditions were presented in blocks and that each condition was presented 3 times. If we now close these windows and click and drag over a new set of voxels, the region of interest signal time course window now shows the conditions as well as the bold response. It is difficult to see how the bold response varies with condition due to the large scale of this graph. However, for now we'll continue with our general linear model analysis. We can do this by clicking on Analysis and going to General Linear Model, Single Study. Here we have a new window shown as our 3 conditions, and what we want to do is to define these conditions as predictors in this model. You can see that these predictors have been defined by scrolling through each in turn. You can also see that the fixation condition has been defined as a predictor. Generally speaking, we don't want to include the fixation condition as a predictor in our model. To fix this, we can close this window and reopen it. And in the Options menu, we can tell Brain Voyager to exclude the first condition as our rest condition. Once this is done, we can redefine our predictors and click Go to start this analysis. Once complete, we can see that Brain Voyager has colored some of the voxels with either warm or cold colors. These correspond to voxels that show an increase or decrease in bold activity compared to baseline for all of our conditions. We also see a new window called the voxel beta plot window, and this shows us for each voxel the beta weight assigned to each condition, where a positive value corresponds to an increase in bold compared to baseline, and a negative value corresponds to a decrease in bold compared to baseline. The change in bold compared to baseline is defined by the magnitude of the beta weight. We can change the information that Brain Voyager shows us by clicking on Analysis and then Overlay General Linear Model. This new window allows us to look at different contrasts between our conditions. However, we're still working with our FMR that hasn't been corrected for magnetic saturation effects, so it's time to correct for those effects and redo this analysis. This time we will skip 2 volumes. If we now use the left mouse button to click and drag a new group of voxels, we get a new region of interest signal time course window, and it becomes much more apparent how the bolt response is varying based on our conditions. You can see clearly from this small group of voxels in the left hemisphere that the amplitude of the bolt response is increasing in response to objects presented in both visual fields and also to objects presented in the right visual field. We can improve the statistical power of our analysis by pre-processing the FMR. To do this, we can click on Analysis and Pre-Processing. And here we want to click on the Advanced button to get details of all the pre-processing steps. By default, we have enabled Slice Scan Time Correction, 3D Motion Correction, and Temporal Filtering. In this experiment, during every TR, or every 2 seconds, the scanner collects data from 25 different slices. These slices are collected one after another during the 2-second TR, creating a single volume. As such, during a single TR, each slice is collected at a different point in time. Slice Time Scan Correction uses interpolation to correct for differences in time for acquiring each slice, such that the final result is now that each slice appears as if it was collected at the same time within a single TR. 3D motion correction uses interpolation to correct for small movements made by the head during the scan. These corrections are made in the X, Y, and Z axes and also rotations about these axes. Temporal filtering filters out noise from the signal. A common cause of nuisance noise is something like scanner drift. A general rule of thumb for determining how many sines cosines to use for temporal filtering is to multiply your number of volumes by your TR to determine how long your experiment was in seconds, dividing this number by 60 to determine the time in minutes, and then halving this number as the number of sines cosines to use. As a passing comment on 3D motion correction, it's always advisable to recruit subjects who are capable of staying still inside the scanner. Data collected from subjects who have moved more than we would like inside the scanner lead to problems with 3D motion correction, which causes problems with co-registration. Motion artifacts become much more of a problem at higher resolutions, so it is advisable to recruit subjects who have a good track record with MRI. When pre-processing is complete, we see a movie of the first volume before and after 3D motion correction. We also see the graph of 3D motion correction showing the extent to which their subject moved within the scanner during the scan. You'll also notice that we've created a new FMR, a pre-processed FMR, containing abbreviations for the different pre-processing steps that we did. We can see the effects for pre-processing steps on the statistical power of our analysis by redoing the general linear model single study analysis. If we compare this with the previous unpreprocessed FMR, it should be apparent that we have many more voxels showing an increase and decrease response to the conditions. If we also select the group of voxels to open the region of interest signal time course window, we can also see that many of the linear trends caused by scanner drift have been removed from the signal. If we again open the overlay general linear model window, we can change the contrast to show us only those voxels that are active when objects are placed in the left visual field. Unsurprisingly, most of these voxels appear in the right hemisphere visual cortex. We can also change the contrast to show us only those voxels that respond to images in the right visual field. And again, most of these voxels appear in the left hemisphere visual cortex. Finally, by placing a cross in the box for images in the left visual field and a minus in the box for images in the right visual field, we can see those voxels that are responding significantly higher to images in the left visual field compared to those with images in the right visual field. And here you can see orange voxels in the right hemisphere and blue-green voxels in the left hemisphere.